All right, and as I mentioned before, I am using a slightly different setup. I'm going to try standing while I lecture just because 5 hours of sitting is rough on my back. I feel for you guys when you've been sitting all through class and you have to sit through a lab lecture. So I'm standing up, so if you have any problems with the audio or the video, just let me know. All right. So here is where we were at last time. We finished up talking about calorimetry, and I know we did it very briefly. We talked about this Q equals MCAT, and we filled into the problem to find the amount of heat, which was Q. So any questions on this calorimetry problem or anything that we did last class? All right, so let's go ahead on, and I'm going to rotate like so. All right, there we go. If I go out of your field of vision, just feel free to let me know. All right, so here is more calorimetry. And again, we're going to use Q equals MCAT, but we're going to do a slightly more challenging problem. Yay. All right, just in case last class you were like, this is so easy. Don't give me easy stuff. I want the hard stuff to practice so I get an A on that exam. All right, so here we have 60 grams of copper, and it's heated to 1052 degrees Celsius. Then it's put into an insulated cup, and the cup contains 160 grams of water at 21 degrees Celsius. And we're going to find the final temperature of the cup, and the specific heat of copper is given. There's also another thing given here. Oops. And that is this statement right here. And this is going to be really important when we set up our equation. Oops. So I'm going to try it one more time here. There we go. All right, so that's going to be really important for us, and that is the heat lost by the copper is the same as the heat gained by the water. So we talked about this a little bit last class. However much heat is lost from that copper has to be received by something, and we're going to assume you've got a perfect calorimeter, therefore all of that heat is gained by the water. So let's go back and talk about what we mean by a calorimeter. So once upon a time we looked at this, and this was our sample calorimeter. And I said that box in the middle, you can think of it like a piece of metal. So this is going to be our copper. And you're putting in hot copper. And what we are assuming is all the heat that's given off is absorbed by the water. Now your calorimeter is insulated, meaning no heat gets out, no steam gets out. So any heat that is lost by that copper must be absorbed by the water. And we're able to tell the difference in temperature of the water by our thermometer. So essentially, we're going to be able to calculate how much heat is lost by the copper, by how much the temperature is changed by the water. So any questions on anything here so far? All right, so let's go ahead and go back to this one. All right, so I'm going to use the formula that we have, Q equals MCAT, and I'm going to use this concept that the heat lost by the copper equals the heat gained by the water. So what I'm going to say is the Q for the copper, that is going to be the heat for the copper, equals the heat from the water. So same quantity of heat, but they need to have different signs because one of them is releasing heat and the other one is gaining heat. Doesn't really matter which side you put the negative on. I'm going to go ahead and put it on the copper because I know copper is losing heat, but again, it doesn't matter. If you decided to put it over here, that's perfectly fine as well. So you have the same quantity of heat, but they have opposite signs because one is losing and one is gaining heat. So any questions so far? All right, so next up, I'm going to fill in here. We know Q equals MCAT. So I'm going to fill in that MCAT on both sides. So first for the copper, I'm going to say negative out here. And then instead of Q, I'm going to write MCAT, but I'm going to say M for the copper. That's the mass for the copper. Specific heat for the copper. and then change in temperature. And what we said about change in temperature is it's T final minus T initial. So put little brackets here, and I'm going to say T final for the copper minus T initial, again for the copper. So that T final minus T initial, that's our delta T, this value right over here, and everything over there has to do with the copper. So any questions on how I expanded the Q for the copper, or I should say negative Q for the copper, into negative MC delta T for the copper? All right, so next up, let's do the same thing for our water. So I'm going to say the mass of the water times specific heat for the water. And then we need our delta T. So this is T final for the water minus T initial, again for the water. And I'm hoping me changing colors is helpful and not too distracting, because I know every time I change colors, it flashes on the screen, that whole box there. So if it gets too distracting, please do let me know. All right, so the right-hand side there, that is MC delta T for the water. So again, all I've done is take the Q that we had before and turn it into MC delta T, and I labeled each one. So on the left side we have the copper, on the right side we have the water. All right, so questions on anything so far? All right, so let's start filling in. As we fill in, I'm going to have to put these two on different lines just because they're going to get a lot larger, but that's okay. So I'm going to say negative, and now I need the mass for the copper. And way up here, the mass was 60 grams. That was 60.0 grams. And that was the mass of our copper. And I'm multiplying it by the C for our copper. And there it is, 0.385. And now it's in joules per gram times degrees Celsius, just like we saw last time. All right, so now I need T final for the copper minus T initial for the copper. So I'm going to go ahead and say T final for our copper minus the T initial. And the initial was the initial temperature when it got dunked into the water. And we were told that was 1052 degrees Celsius. Now, last class we talked about how I have been torturing you with kelvins, and that was for chapter 5 or gas laws, but nothing here involves gases. So we need to stay in Celsius here. And one trick that I told you last time to help you remember that we're in Celsius is to look at the units of your specific heat. And that says Celsius there. So we do need to stay in Celsius here. So 1052 was our initial temperature. All right, any questions on how I filled that in there, or about why we're in Celsius, not Kelvin, or anything else? All right, so next up we're going to fill in for the water. We need our mass of water. And it looks like our water was 160 grams, or 160.0 grams. All right. C for the water, it wasn't given here, but it was a value I told you you'd need to know. Does anyone remember what C for water is? Thinking way back to last class? Way back. All right, so let me remind you. I see it looks like there's 1,00, which I think might be 1.00, which is for our calories, but anybody remember for joules? Starts with a 4. There it is, 4.184, excellent. All right, so 4.184, and now it's going to be those same units of joules divided by grams times degrees Celsius. So when we're doing these, we will usually be in joules, and we're going to want that 4.184. So let me put a note right here. Oops. One more time. And I want you to know this value. So know C for water. So know the specific heat of water. Let me actually write that out. So know the specific heat for water. There we go. All right. Any questions on anything so far that we've done? All right. So next up, we're going to have our T final for the water minus T initial for the water. So let's go find our T initial for the water. And initially it's at 21 degrees Celsius. And again, we're not in gas law, so we're going to leave it in Celsius. Like so. All right. Questions on anything that we've done so far? All right, so now we have one more thing that we need to talk about. Go ahead and put in green. All right, so I want to talk about the final temperature. And I want to go back for just a moment to this picture. All right. So originally we start off with our copper, and the copper is much hotter than water, and so we would expect the heat to transfer from the copper to the water. But once it is all done, they're going to get into what we call thermal equilibrium, which is to say at the end of the experiment, they should have the same temperature. So let me put a note here. So at the beginning of the experiment, the way I've drawn it here is the metal is hotter than the water. However, at the end of the experiment, they should have the same temperature. And just to put this in mathematical terms, T final for the water will equal T final for the metal. So the idea is they'll keep exchanging heat until they become the same temperature. And that's something we're going to use in our equation in just a moment. But any questions on anything that I've written here so far? Anybody need this slide a little longer? All right, so let's go ahead on to that final temperature, and what we said is T final for our copper should equal T final for the water, like so. So we're going to simplify our equation in just a moment, but any questions on what we've done so far? All right. So the first thing that I'm going to do to simplify is I'm going to go ahead and multiply all of this part together. All right, so negative 60 times 0.385, and it looks like I've got negative 23.1, so let's write that in. So negative 23.1. And if we cancel out our grams, we're going to have joules divided by degrees Celsius. By the way, it's fine with me if you don't want to put these units in the middle of the problem, as long as you end up with the correct units at the end. So if it's just going to be too confusing for you to figure out those units in the middle, don't worry about them. All right, so next we have T final, sorry, T final minus 1052 degrees Celsius. All right, and notice I dropped T final for the copper. It's just T final overall, because both of the final temperatures are going to be the same. So any questions on what I've done there to simplify, let me get it all on the screen at once, to simplify the left side of that equation? All right, let me. All right, so next up we're going to simplify the other side. So I'm going to take 160 times 4.184. All right, so 160 times 4.184. And it looks like that is 669.44. All right, and so this will be multiplied by TF minus 21 degrees Celsius. Okay, so questions on anything that we've done here to simplify? Oops, I guess I forgot to put in my units. All right, so any questions on anything here? All right, so would you guys like to solve this together, or do you want to give it a shot on your own first? Let me rephrase. Anybody want to give it a shot on their own first before we calculate it together? All right, so a few of you want to give it a try. All right, so let's take a couple minutes. Go ahead and give that math a try. Again, feel free to leave off the units if you'd like to, and then we'll solve it together. So feel free to message me if you have any questions while you're working. Don't forget about your distributive property. Those of you who are looking at this, like that's the ugliest algebra I've ever seen, just feel free to hold on and we will do it together in just a few minutes. So again, if you have any questions on this or anything else, feel free to message me. All right, so I'm gonna put that poll up on the screen. Go ahead and click in if you'd like more time or if you're ready to go over it. Can you all see that poll? Oh, nope, you guys can't see the poll? Okay, let me try one more time. Uh-oh. Let's see. All right, so is it not popping up again? No, okay. I'll have to figure out what's going on with our poll. All right. So, let's see. It's weird. Okay. Would anybody like more time on this one? It looks like our poll is not going to be working for tonight. I'll try to fix that. Yes, more time. Okay. Go ahead and take a little bit more time. Okay. Strange. All right, so I know some of you are still working. Those of you who are finished, feel free to go ahead and type in your value for TF so you could compare answers. All right, so it looks like Tasso got 55 degrees. So if anybody else got something similar or different, go ahead and type in. All right, and it looks like Angie got something similar. All right, so how are we doing? Would anybody like some more time on this one? Okay, so let's go ahead and give this a shot. So we're going to use our distributive property. So we'll be multiplying the 23.1 in to both the TF and to that 1052 degrees Celsius. Then on the other side, we're going to multiply this 669.44 in to both the TF and to the 21 degrees Celsius. So I'm going to start on the left side. So negative 23.1 times TF is just going to be negative 23.1. And just for now, to make our life a little easier, I'm going to drop the units. We'll bring the units back at the end. And then we have negative 23.1 times 1052. And it looks like we got negative 24301.2, like so. All right. Did everybody get something similar at this part? Yes. Okay. So now, just to make our life easier, I'm going to simplify that minus a negative, and I'm going to say negative 23.1 plus 24301.2, like so. All right. Any questions about what I did? Can I type it as a positive? Yes. So it is a positive. So that's why I combined the negative and then another negative. Okay. But yeah, Jervin, if you recognize that straight away, that a negative times a negative will be a positive, yeah, go ahead and put the positives right into your calculator. All right, so on the other side, we're going to have 669.44 times our TF minus 669.44 times 21. And it looks like I'm getting 14,058.24, just hanging on to all my sig figs. Those of you who calculated that out, did you get something similar on the right-hand side? Yes, no, maybe? Okay, yes, thank you. There we go. All right, so any questions on anything that we've done so far here? All right, so now what I'm going to do is bring things over. So I'm going to subtract 24,301.2 from both sides. And on the left, it's going to cancel. So we're going to get negative 23.1 equals 669.44 TF minus, and we're going to have 1458.24 and 24,301.2. And if I did all that correctly, it looks like we've got 38,359.44. All right, did everybody get something similar to that at this point? TF. Oh, I dropped a TF, thank you. The TF that I dropped is this one right here. Thank you very much. All right, so other questions or anything different you guys are getting here? All right, thank you for that correction, Jervin. All right, so next I'm going to subtract 669.44 TF from both sides. And on the right side, that'll cancel. And on the left side, I'm going to combine 23.1 and 669.44. And it looks like we're going to get negative 692.54 TF equals negative 38,300. Keep wanting to put the 5 first. 359.44 like so. All right, and lastly, we're going to divide over the negative 692.54. And for our TF, it's going to be 38,359.44 negative divided by our 692.54 negative. Oops. One more time, 38,359.44 divided by our other answer, and the negatives will cancel out, and we end up with, looks like 55.4. I'm going to check our sig figs in just a moment, but this temperature is in Celsius. Any questions on the math so far? All right, so let's go back and check our sig figs. And there was a lot of math involved here, so I'm just going to go ahead and check our original sig figs, and it looks like we're in 3 sig figs from those grams, the 60.0 grams. So I'm going to go ahead and leave this at 55.4 degrees Celsius. Let's see. Oh, you're right. We had a 21 degrees Celsius. You're right. I forgot about that 21 degrees Celsius. We are down to 2 sig figs. Thank you, Tasso. Yes, I was looking up here and I missed the 21 right over here. And you are correct. That 21 gives us 2 sig figs. I was looking at that 23.1. All right, other questions about our answer, the algebra, or how we set this one up? All right. So next up, we're going to talk about enthalpy. So enthalpy is heat or energy, and it's going to be the change in that heat or energy we see in a chemical reaction. So the change of enthalpy, we're going to see it as this delta H, and we're going to see delta H quite a lot. So I do want you to know enthalpy as a vocabulary word, one way to remember that we use H for it, which sounds weird because we would think, hey, why not E for enthalpy, is to remember that it has to do with heat. So it's heat or energy that's going to change throughout a chemical reaction. And the units that we're going to use overall could be joules, kilojoules, or calories, but what I'm going to tell you is in this class, we are primarily going to be looking at joules or kilojoules. All right, so questions on anything here with the enthalpy? All right, so here is an exothermic reaction, and I think I talked to you a little bit about exothermic reactions at the beginning of this chapter. So an exothermic reaction is a reaction that gives off heat. So again, that's the image from our famous gummy bear video from day one, the gummy bear torture chamber. But it is an example of an exothermic reaction. So any reaction that can give off heat, it can give off light, it is giving off some kind of energy, that is exothermic. So I like to remember exothermic as in the word exit. So something is exiting the reaction. It could be heat or it could be energy. All right, so if you have an exothermic reaction, it is going to release heat or energy to the surroundings, and to your hand, it's going to feel warm or hot. So this is not something you've heated up over a Bunsen burner or a hot plate. It is something that got hot all on its own without you having to do anything. And we are going to say that it has a negative enthalpy. So the reason we say it is negative is because it has lost heat or energy. So if you remember way back to when we were talking about potential energy, the energy that is stored in the chemical bonds, it is being released. So originally, our gummy bear, if you will, had all this energy inside of it. Once it has gone through its reaction, that energy is no longer in the gummy bear. It's been released outside as heat, as energy. So when we release our energy, then we are essentially losing it. So we always talk in terms of our chemical reaction. That is to say, we talk in terms of the system. Whatever's in your beaker, whatever's in your test tube, that's always our reference point, not where the people are standing, because in chemistry, who cares about the people? It's all about what's inside of your beaker. All right, so this is your system right here. And if that system loses its energy or heat, then we say it is negative. And that's what we have in our picture. Heat is moving out of the reaction, so it's moving out of the system. And I'm going to show you a graph, which I think will help with this in just a little bit. But any questions so far about the idea of the exothermic reaction? Heat or energy has been lost, and therefore we refer to it as having a negative delta H. All right. So next up is an endothermic reaction. Endothermics are a little trickier. So when I hear the word endo, I think of the word enter. So heat or energy is entering this reaction. So it needs to gain that heat or energy from the surroundings, and because it is gaining, heat or energy, we give it the positive delta H. We say it has positive enthalpy, and so here it's represented with this arrow. So heat or energy is coming in. Now, most of the time when you have an endothermic reaction, you have to heat it up. And you've done this, well, I think we got a chance to do this in class. Normally at this point I could say you've done it in lab, but we've used our Bunsen burners. So yes, I think you have done this in lab. So this is what's going to happen most of the time. So most of the time you have to apply heat or energy. So that means that it's over a Bunsen burner, it's over a hot plate, somehow you have given it that heat. So it may feel hot to you, but again, only because you gave it the energy. There is another way though. I'm hearing an echo, so I think I'm gonna mute everybody. But feel free to unmute if you have questions. It's just I was hearing an echo for a moment there. All right, so there is another way, and that other way is right here. So sometimes you have a very industrial set of chemicals, and they can essentially reach out and grab the heat that they need. And these are things that will feel cold to your touch. And an instant cold pack is one of those things. So inside of there, there are two chemicals. When you are ready to use it, you twist it, you break the inner seal, and they start to react. It's an endothermic reaction. It needs heat, but where it's going to get the heat is actually from your arm. So right over here, it feels cold to the arm, and the reason is those chemicals, they aren't going to wait for a Bunsen burner. They're just stealing it right off of your skin. And we have a few, very few chemicals that can do that. So if something were to feel cold to you, it is stealing the heat right out of the air or off of your skin if it's against your skin. But again, very few can do that. Most of the time, we have to actually apply heat. But endothermic gets a little tricky when you're actually in the lab because it can feel hot, but it only feels hot because heat has been applied. The exothermic, you never would apply heat to it. It generates heat on its own. All right, so questions on anything here about the difference between the endo and exothermic reactions? All right, so next up, we are going to talk about energy diagrams. And I do want you to be able to draw and label the energy diagrams or to look at an energy diagram that I draw and understand what I'm saying. So let's give this a shot. So I'm going to start off with an exothermic energy diagram. And remember, exothermic means exit, so heat or energy needs to be leaving this chemical reaction. And I'm going to draw a graph here, best as I can. All right. So here on the left-hand side, we're talking about energy or heat. I'm going to go ahead and call it energy. And down at the bottom, I'm going to say reaction progress. And if I haven't used it before, RXN is an abbreviation for reaction. All right. So here are my reactants. Change to a thinner pen here. All right, so in an exothermic reaction, heat or energy is leaving. Therefore, your products will always have less energy than the reactants. So I'm going to put my products right down here. All right, any questions about why the products are lower than the reactants in an exothermic reaction? Okay, so just to illustrate the idea that the reactants are losing energy, we usually draw an arrow right here. And let me actually draw the arrow completely from the reactants down to the products. So the amount of energy that was lost is from here down to here. And that is what delta H measures. So here I'm going to say negative delta H. So the amount of energy, again, between the reactants and the products, that is your enthalpy. That is the amount of energy lost. And we emphasize the fact it's lost by calling it negative here. So soon we're going to get into some calculations. And anytime you see this negative, you're going to know you're looking at an exothermic reaction. So any questions so far on the exothermic? All right, so let's do our endothermic next. All right, so I'm going to go ahead and zoom into our endothermic. There we go. All right, so I'm going to go ahead and put my reactants in the same spot, somewhere in the middle. I don't have to put it in the middle, but I just wanted to show you that it doesn't matter where the reactants are. Now this is endothermic, so heat or energy needs to be entering. So we're going to see our products at a higher level. And let me go ahead and label this with energy. on the y-axis and reaction progress on the x-axis. So for our arrow, we're going from the reactants up to the products, like so. So the difference between reactants and products in an endothermic is also called delta H, but now it'll be listed as a positive delta H because that energy is being gained. All right. Any questions about that endothermic or the exothermic reactions? Or any questions about enthalpy, positive, negative, when something's exothermic or when something is endothermic? All right, so let's go ahead and take our break, and it's almost 5:50, so let's go ahead and come back at 6 o'clock, and I will be here if you have any questions. Feel free to type in or just unmute yourself and ask. All right, let's go ahead and get started again. All right, so any questions from before break? All right. All right, so before break, we were talking about enthalpy. Way back up here, we said that enthalpy was delta H. So enthalpy is the difference in energy between the reactants and the products. And again, you can think of it as energy or you can think of it as heat. Sometimes it's helpful to think of it as heat because our symbol is an H. And over here we said that if you have an exothermic reaction, it's going to lose energy or heat. And so that's why we refer to it as negative enthalpy or negative delta H. And for endothermic, we said it's going to gain heat or energy, and therefore we refer to it as a positive delta H. Now I want to talk to you about some types of enthalpy, and I don't want this slide to scare you. They're all the same enthalpy. They all mean the difference in energy between products and reactants. The first one is just a general way of phrasing it. Delta H reaction means it's delta H for any reaction that you might have. This could be an acid base, this could be a combustion, this could be your favorite gummy bear being dissolved into potassium chlorate, any kind of reaction you want. There it is, delta H reaction. Now for the other ones, what you're going to see is a subscript, which are these small letters here, that just tell you what kind of reaction. So for a lot of reactions, we just like to be more specific. For instance, that delta H comb is actually delta H combustion. So you can go online and you can look up tables of delta H comb or heat of combustion, and you're going to find the values for the combustion of lots of different compounds. But usually if you're looking for a specific delta H, you want to look it up because you need it in your research. You're going to look it up on a table that's specific to that type of reaction. So again, the heat of combustion reactions will all be listed on a specific table, and that table will be labeled delta H comb, meaning delta H combustion. Underneath, we see the delta H of neutralization. And neutralization means our acid-base reaction. So again, let's say you want to know what the delta H or the enthalpy will be when you react HCl to NaOH. You're going to look it up on a delta H of neutralization table. So it's the same delta H that you would see in delta H reaction, delta H combustion. It's just with the neutralization, it's specific to the acid-base reactions. And by the way, underneath neutralizations, let me go ahead and write out acid-base reaction, just to remind you that that's what we're talking about with the neutralization. All right, so underneath there we have delta H vape. Don't worry, it's not bad for its health. It's not really vaping. So this is delta H of vaporization. And what we know about vaporization is it's like boiling. So it is liquid going to a gas. That's our vaporization. So if you're dealing with the delta H of vaporization, again, it's just a very specific type of reaction, and that reaction could be referred to as boiling or vaporization. All right. By the way, if the audio or the video starts getting funky, just let me know, because I'm standing in an area that might be a little tougher to get to my get the internet from my router. So just let me know if any of that happens. All right. So what I just highlighted, delta H fuss, is delta H of fusion, and fusion is also known as melting. So by melting, we mean a solid going to a liquid. So again, just means a difference in energy between products and reactants, but this is specific to something that's melting. And finally, at the bottom, we have something that we're going to talk a lot more about, and that is the delta H of formation, where this little circle, which is called a knot on the top, refers to something in its standard state. So what we're going to find, and again, we're going to get way more PowerPoints on the heat of formation, but this is, again, difference in energy between products and reactants. But in the case of the heat of formation, it's going to be forming something from its standard state. So the way you would find it in nature. And I'm not going to go into too much more detail here because, again, we're going to get to it in just a little bit. Any questions on anything from this lovely list of enthalpies? All right, so again, I don't want you to get scared off. I know it looks like a huge list of horrible things. This is not something to memorize. It is just to make you aware of things that you might see in this class, in a textbook, or in future classes. All right, so back to everybody's favorite, some math. So we're going to do stoichiometry with our enthalpy. So here it says calculate the heat associated with a complete reaction of 364 kilograms of ammonia according to the reaction below. All right, before we do that problem, I want to talk about that delta H value. So I'm going to go ahead and copy all of this down, and we're going to just kind of dissect this a little bit. I always feel bad when I use biology terms because I know some of you are like, hey, that's not what dissection means. Anyways, all right. So first off, reaction. So this is just saying, hey, in general, for the reaction we have, this is the difference in energy between the products and the reactants. Then I see a negative over here. What is that negative telling us? Give you a hint, it's either endo or exothermic. Everybody's so shy today. Anyone want to give it a guess? Is this endo or exothermic? Exothermic, excellent, thank you guys. Yes, exothermic. So this is going to be exothermic because it has a negative delta H value. Anytime you see negative delta H, you know that value, and just for the fun of it, if you wanted to, you could draw out its graph. So reactants, products, going down, I'm going to say energy, and reaction progress. Let me zoom in for those of you who are on cell phones, because I know that could be pretty small. As soon as I know it is negative delta H, I can draw out that graph. Just a very simple graph saying that we have reactants above products, and we are going down, and this is a negative H value. So any questions about how I was able to tell so much about this reaction just from that negative sign? All right, so the next thing I want to talk about is the stoichiometry of this reaction. So the way I have your delta H value written here, it is negative 906 kilojoules. Now, in most textbooks, you're going to find this as kilojoules per mole. But there's a reason that I don't do that, and it's not just laziness. Might be laziness, but there's another reason too. And the reason is when we see kilojoules per mole, a lot of times we think, hey, that must be 1 mole in the denominator because that's what I have taught you and I've drilled into your head. And the reason I leave it out is that it is no longer 1 mole. It is per 1 reaction. So in other words, it's 4 moles of NH3 or 5 moles of O2, 4 moles of NO, or 6 moles of H2O. So let me show you how this works. So I could say negative 906 kilojoules per 4 moles of NH3. So again, it's not 1 mole, it is per reaction. And this reaction was balanced with 4 moles of NH3. Therefore, we need 4 moles of NH3 if you're using this as a conversion factor. So any questions on what I just did with that NH3? All right, so this is something you definitely want to get some practice on because it trips a lot of people up because we're so used to saying 1 mole in the denominator. It has to be per coefficient in the balanced equation. Let's go ahead and write out some more. So I could say negative 906 kilojoules per 5 moles of O2. And those 5 moles, again, are coming from our balanced equation. I could also say negative 906 kilojoules per 5 moles of NO. I'm sorry, 4 moles of NO, and that 4 moles coming from our balanced equation. Or I could say negative 906 kilojoules per 6 moles of H2O. So the deal is, if you are given an amount of anything in your chemical reaction, in this case, ammonia, oxygen, NO, or water, you can figure out the amount of energy if you have delta H, or if you're given the amount of energy using delta H, you could figure out the amount of moles or grams using any of those chemicals in that balanced equation. So this topic tends to be trickier than it looks at first glance. But any questions about that idea that we're not saying it's per 1 mole, we're saying it is per however many moles were in that balanced chemical equation? And yes, Juan, these are conversion factors, exactly. So we will need delta H as a conversion factor. Other questions? The one nice thing about my new setup is I'm not constantly looking up to the right hand of the screen for the chat box. All right, so let's go back to our problem. So here it says calculate the heat associated with 364 kilograms of our ammonia according to the reaction below. So I'm going to start with the amount we're given, 364 kilograms. And now we need to get this into our kilojoules. But first, what we know is that delta H has to do with moles. So we are going to need to get our ammonia into moles. First thing I'm going to do is turn it into grams. So I'm going to go from kilograms to grams. Anyone remember that conversion factor? All right. So I see, yes, so I see the 1000s. Do the 1000s go with the grams or the kilograms? Excellent, grams. So there are 1000 grams in 1 kilogram. So one of the ways that I remember where that 1000 goes is I think about what a gram would be like in real life. And a paperclip is about 10 grams. So when I think about a gram, I think about a paperclip. And a brick would be on the scale of a kilogram. So when I think about paper clips versus a brick, and truthfully I don't think 1000 paper clips really make a brick, but something in that range, you would need a lot of paper clips to equal a kilogram, to equal a brick. The other thing, and I think I've mentioned this, one of our awesome tutors came up with this idea, and what they said is that you always put something big with something small. So 1000 is a big number, and a gram is very tiny. Again, it's on the scale of a paper clip. So 1 is a small number, and it goes with something very big, which is a kilogram, which is on the scale of that brick. So you always put something small with something big. So sometimes that can help you remember where to put that 1000. Those of you who are like, please, I'm an expert on where to put the 1,000, just totally ignore what I said. All right. So we're going to have to get into moles, so we are going to do our conversion, and this is going to be between grams of NH3 and 1 mole of NH3. So let's go ahead and do this together. There we go. So we're adding up NH3 for our problem. So here's our nitrogen, 14.01, plus 3 oxygen, so 16 times 3. And for those of you calculating out on your, I would say at home on your own, did you get about 62.01? Anybody get 62.01? Or anyone brave enough to calculate out that NH3? Oh wait, I'm sorry, I calculated out NO3, not NH3. Let me try that one more time. 14.01 plus 3 times 1.008. All right, 17.034. Does that sound better? Yes, all right, thank you. And I liked Juan's comment of just the question mark, yes. Sorry about that. I don't know why I was so excited about putting the oxygen in there. So no, it was NH3. I calculated out NO3 by accident. All right, 17.0, and I'm going to go ahead and say 3,4 there. All right, so now that I've calculated it correctly, everybody get something similar? All right. All right, so here is the new piece for our stoichiometry. So now we have moles, NH3, and we're going to have kilojoules up in the top. All right, so I'm going to go ahead and say negative 906 kilojoules. And what about the bottom? What number goes here with the NH3? And it looks like Dravin has a 4, and looks like lots of 4s coming through. Excellent. Any question about that 4? Any question why it's not a 1 or some other number? All right, so go ahead and take a moment and calculate out our kilojoules, and it will come out to be a negative number here. All right, so what are you all getting? Looks like it's going to be a pretty big number. And you want to bravely type their number. All right, so I'm seeing 4.84 times 10 to the 6 negative. All right, excellent. Look at all those wonderful numbers coming in. Any questions on how to calculate that number, or anybody getting something different? All right, so I want to talk about this negative sign a little bit more. Let me open up a new page for us. By the way, if you're thinking, oh my gosh, that's a huge amount of kilojoules, it is, but 364 kilograms is a huge amount of NH3. But let me go ahead, paste this in here, and I want to talk about that negative sign here. So we know that the negative sign tells us it's exothermic. But the other thing I need to tell you about that negative sign is that negative sign is directional. So those of you who've had physics, you know about vectors and you know about the difference between speed and velocity. So if I said, hey, I'm going 25 miles an hour, actually now if you're driving, there's not many cars on the freeway, you can go faster than 25 miles an hour. But let's just say my speed is 25 miles an hour. That is different than saying the velocity. If I said, I am going 25 miles an hour north, it is now a velocity. It has direction. So what that negative is it gives us direction. And I know people hate this. Sometimes in chemistry, we make our negatives just disappear. I know math teachers, it would give them a little heart attack to hear this. But sometimes we do. So what I'm going to tell you is, yes, the negative tells us it's exothermic. It tells us that energy is given off. But if I just asked you how much energy there is, you are welcome to tell me 4.84 times 10 to the 6 kilojoules. That is how much energy is given off. When I say given off, oops, sorry, that's the one I wanted. When I say given off, I am saying the negative. So when you see a chemistry problem, whether it's in a textbook or somewhere else, sometimes they will use the word given off to replace the negative sign. And that's really frustrating to students because you want a consistent negative for everything that's exothermic. But because we are mean, cruel, horrible people, sometimes we use those words given off to indicate the negative. Now we're going to get to a problem next where you're going to be converting energy into grams. Remember, you can never have negative grams. So what I'm going to tell you here is that you can always tell me the energy in positive terms. Even if it's an exothermic reaction, you can always refer to it as positive. And that is because I don't want you guys to get turned around about whether it's negative or whether it's positive. So I hear a question, so negative can never be used for energy. So no, actually negative is used very frequently in energy, and it's just showing you the direction that it's being given off. Negative could never be used for grams. It could never be used for a physical quantity like grams, like liters, but it is used in energy. So again, for the energy, you are welcome to report this as positive or negative because I don't want you to get stuck on that negative. So let me write this out for you. So energy, and by energy, I'm going to say joules or kilojoules, really calories as well, but we won't be dealing very much with calories. So you can report the energy, joules or kilojoules, in positive if you want to. For a lot of students, that saves them a lot of angst about worrying about whether it is positive or negative. There we go. All right, so you are always welcome to report energy as positive to me, and be aware that when you're reading a textbook problem, it is considered repeating yourself to say negative kilojoules is given off. So that is why they will either put the negative or given off. But again, I'm not here to teach you grammar. So if you just want to report it as positive, that's perfectly fine with me. I know that it's kind of a weird talk about direction and such, but any questions about what I just said? All right, those of you who want to just completely block out everything I said about direction and just remember the part in the box, you are welcome to. Just remember, you can always report energy to me as positive. So when in doubt, just feel free to give me a positive number. Okay, any questions on what we did here in terms of how we set up those conversion factors? And I remember earlier we had a question about delta H, and yes, delta H can be used as a conversion factor. All right, so here it says how much methane in grams is required to release 4.42 times 10 to the third kilojoules of heat. And here we have a delta H comb that is telling you delta H combustion of negative 802.3 kilojoules. So first up, we have to set up our chemical reaction. So we have CH4 and it's undergoing a combustion reaction. So what other reactant do we need? All right, so I'm seeing O2, excellent. Any questions about how we knew we would need to add O2 to a combustion reaction? All right, so what are our two products here? All right, so I see CO2 and H2O. Excellent. All right, so what I'm going to ask you to do is balance out this equation and then try to do the stoichiometry, very similar to what we did way up here. And one hint that I want to tell you is make your grams, which is what you're looking for, positive. Grams are a physical quantity we weigh out. We could never have negative grams. So even though your calculation will turn out negative, make them positive. So give this a shot. Again, you're going to balance your equation. And then you are going to solve for your grams. And you're solving for grams by setting up that stoichiometry just like we did previously. And as always, if you have any questions for me, feel free to type into the chat or unmute yourself and talk. And always feel free to chat with each other. So on the drop-down menu, you can choose who you would like to chat with. I won't be offended if you cut me out of the conversation and choose your best friend in class or your lab partner. So I know most of you are still working. Anybody want to put in their balanced equation though, so we can make sure everybody has a properly balanced equation? Very brave and proud of their equation. All right. Thank you, Angie and Juan. So it looks like we got a 2 in front of oxygen and a 2 in front of water, and that looks correct. All right, so check your balancing. Make sure you have the correct balancing for your equation. If you have any questions on how to do it, feel free to type into the chat or unmute and ask questions. And it looks like Tasso has the same thing. Excellent. You're also, of course, welcome to select one of these wonderful people who put up their equation, Angie, Juan, or Tasso, and be like, dude, you're so smart. Can you show me how you did that? All right, and it looks like Dervin has an answer. Anybody else have an answer and you want to share with the group and compare answers? All right, it looks like Clinton has an answer too. Anyone else want to confirm or deny what Clinton has? So Dervin, I know you shared just with me. Do you feel comfortable sharing with everyone or just with Clinton? All right, Clinton, hang on. I'm sure. There we go. All right, so we got Clinton and Jervin have answers. The rest of you are still working. Go ahead and keep on working for a little bit. And if you get an answer, feel free to type in and confirm or deny what Clinton and Jervin have. And it looks like Tasso and Juan have something similar. All right, so let's take about another minute or so, and then we'll go over it together. Sorry, the poll is not working, so I don't have the poll to check to see if everybody's done. All right, it looks like Kristen's got a similar answer. All right, so how's everybody doing? Does anybody want some more time for this problem? So I can't see your pencils moving, so I'm going to have to trust that if you're not typing into the chat that you don't need more time. And I will get that poll fixed for next time. That way everybody could just click in to let me know. All right, so let's go ahead and give this a try. So we're going to start with the number that we're given here. This 4.42 times 10 to the third kilograms, I'm sorry, not kilograms, kilojoules of heat. So 4.42 times 10 to the third kilojoules of heat. And we know we're trying to get 2 grams of methane. So I'm going to start with that delta H value. Now when I put it into the bottom over here, if you're thinking ahead and you're like, hey, I know I need grams, I know it's got to be positive, you can just leave off the negative here, or you can take off the negative at the end. So it's your choice whether you want to take off the negative here or at the end. Since I've already determined that grams must be positive, I'm going to just take off my negative here. But any questions about that, about taking off the negative because grams have to be positive? All right, so on the top, we're dealing with our methane. And we need to go into moles of methane. Since we have an invisible one here, I'm going to say 1 mole. And next up, we need to get into those grams. So we're going to use our molar mass. So for every 1 mole of CH4, how many grams of CH4 did y'all get? All right, so I'm hearing 16.042. That sounds like a good molar mass. Like so. All right, and then you calculate it out, and it looks like the popular answer was 88.4 grams. And I also see it written as 8.84 times 10 grams. Either of those work. So this is how much methane we would need for that many kilojoules of heat. So any questions on this problem? So this is actually a very useful problem. So methane is used in our Bunsen burners, but it could also be used for heating in a barbecue situation or other type of situation. You may know how much heat you need for a specific experiment. So you may need to calculate how many grams of methane you need to make sure that you have enough if your methane is not piped in as it is for our Bunsen burners, but maybe you actually have a canister that you buy of methane, whether you buy it at the camping store, whether you buy it at 7-Eleven. You might need to say, hey, I'm going to need this much methane, so I need to make sure I have enough in my canister. So very, very useful kind of problem. Your friends and relatives will think you're super cool when they're barbecuing and you're like, hey, would you like me to calculate how many kilojoules of heat you can get out of that canister of methane? They really will think you're cool. All right, questions about this problem? Thanks for laughing at my bad jokes, Tassa. All right, so next up, we are going to talk about what we call a state function. So a state function is independent of path. It means it doesn't matter how you get there. The only thing that matters is that you got there. So I have these two pictures here. One is somebody rushing up the stairs, and the other is people packed into an elevator. So you all know that after lecture, we would normally go over to the lab building, and we've got to get from the first floor to the third floor. Now, if I talk about the vertical distance from the first floor to the third floor, it really doesn't matter whether you took the stairs or you take the elevator. Oh, I see Jervin has a question on the previous problem. Just give me a moment, Jervin, and we will go back. So it doesn't matter in terms of the vertical distance, which way you go. If you choose the stairs or the elevator, either way, we're all going to get from the first floor to the third floor. So that vertical distance is a state function because it doesn't matter what path you take. However, you all know that work is not a state function. So you know you're going to get much more work taking the stairs, especially if you run up them like this guy is. So I know I usually take the lazy way and I take the elevator, but I go through less work. But no matter how much work we go through, we all get to the same vertical distance. So we always start with the initial location of the ground floor, and we end up at the final location of the third floor. So that is what we mean by a state function. It doesn't matter how you get there. It just matters what your initial state was and what your final state was. So we're going to use this in an upcoming problem. But any questions about that idea of a state function, where all we care about is your initial and your final position? All right. And now Jervin had a question on the previous problem. And no, it does not have to be 8.84 times 10 grams. It's just that some people wrote it that way. So I just wanted to write the two answers that I saw on the chat box. So either way is perfectly fine. All right, other questions either on this enthalpy problem or on that state function? All right, so if you're thinking, wow, state functions are so cool, I can't wait to use them. We're going to use them in something called Hess's law. So Hess's law is extremely important. So when I say extremely important, I mean you have a close to 100% chance of seeing it on the exam. The other thing is that those of you going into Chem 1B, you often see this in Chem 1B as well. So sometimes when I start talking about Hess's law in Chem 1B, I see eyes rolling and I hear groans and they're like, oh no, not Hess's law. And so what I'm going to tell you is that if you master it now, it will pay dividends both in the exam coming up and next semester. It is not that hard to master, so I just want to encourage you to put that extra work in to learn Hess's law now and not let it become that thing that you dread every time it comes up. Also, interesting side story, I once had somebody sub for me whose last name just happened to be Hess, and I said, Dr. Hess will be subbing for you tomorrow, and everybody was like, oh my gosh, is that the Hess of Hess's law? And no, her last name just happened to be Hess. Anyhow, back to chemistry. So Hess's law is about enthalpy. So enthalpy is a state function. We don't care the path it took. All we care is where did your reaction start out and where did your products end up. Next semester, when you get into kinetics, you're going to learn what actually happened on the path. But again, for us, all we care about, where did you start and where did you end up? We started on the ground floor of the D building, we get to the third floor. And it doesn't really matter if you take the elevator or you take the stairs. Same thing with Hess's law. All we care is that where we started and where we ended up. And so we use the fact that enthalpy is a state function. All right, so what we're going to be doing is we're going to be adding delta H overall for the reactions, and basically the overall reaction will equal the sum of the steps. I know it sounds kind of crazy right now, but I'm going to go through an example with you. So we are going to essentially break our chemical reaction into smaller reactions, what we could think of as steps that will help us to get from our reactions to our products. But the great thing about Hess's law is they don't really have to be real steps. They don't have to be steps you actually did in the lab. As long as mathematically they add up to your overall reaction, you are good to go. All right, so again, we can break down a reaction into individual steps that might or might not have happened. All right, so here's what I mean. This is our overall reaction. Carbon is graphite, going to carbon as a diamond. So carbon is graphite. If you didn't know, that is more commonly known as your pencil lead. So inside of a pencil, it's not real lead, it's actually graphite. So this is the chemical reaction that shows that graphite that's inside of your pencil becoming a diamond. That would be super nice, right? If you could take your pencil and somehow magically make it into a diamond in the inside there. All right, so here we have a couple reactions. I'm going to call them 1 and 2. The first reaction says graphite interacts with oxygen to form CO2. And the next one says CO2 would then break down into a diamond and give off oxygen. So we're going to be setting up reactions like this. And the last thing that we will be doing is anything we see on the left and again on the right, we're going to cross out. And then we're going to add up what we have left. Oops, sorry, there's one more I didn't cross off, and that is the CO2. Then we're going to add up what we have left. So carbon is graphite, and carbon is a diamond. So we cross out anything we have on the left, and again on the right, we bring everything else down, and then we will add up our delta H values. So I'm going to show you how to do this in more detail. But any questions on anything so far? Okay. So I know it sounds a little crazy when you first see it, but trust me, it's not as bad as it seems. All right, so here is the same problem we looked at before, but I've written it out with the delta H values. So this is what we want right here. And I will always give you the reaction that we want, and we call it the overall reaction. And I will also always give you the individual reactions. I'm going to call this one 1, and I'm going to call this one 2. Sorry, I added that page into the wrong place. There we go. All right. So now what's different between what you're looking at now and what we just did is that most of the time you're not going to be able to just easily cross things out. You're going to have to figure out what to do with these reactions. Sometimes you're going to have to flip them over. Sometimes you might have to double them. Sometimes you might have to cut them in half. So let me show you how that works. So my recommendation, and Hess's law is kind of like balancing chemical equations. There's a million ways to do it. If when I'm done with this, you're like, oh my gosh, that makes no sense. Feel free, I won't be offended if you Google it and you watch some YouTube videos on it. Everybody has their own method for doing it. So what I'm going to do is say, hey, look, there's graphite on the left, and I look for it below, and I find it right over here. And then I look to see if there's any other ones, and there are not. This is the only graphite that I see in reactions 1 and 2. Now I ask myself if it's on the correct side of the equation. That means, is it a reactant or is it a product? The correct side is wherever it is in the overall reaction. So the way you want to think of the overall reaction is this is the correct equation and we are building it from what's below. So I see this graphite here on the left. This is also on the left. That looks good. Now I see that I have 1 graphite. Remember, if there's no number, we assume it to be 1. And I see that there's no number here, so I assume it to be 1. So the graphite in reaction number 1 is on the correct side, and I have the correct number. So it is correct as written. So I'm going to rewrite these. I think it's easier to always rewrite them, so I'm going to recommend that. But the first one is correct as written, so I'm just going to go ahead and recopy it. And I'm going to say G, and I'm just going to abbreviate graphite there, plus O2 goes on to CO2. And here's our first delta H value, negative 393.5 kilojoules. So it was correct as written, so I'm bringing it down. But any questions on how I determined it was correct as written? Any questions on it being on the correct side or having the correct number? All right, so let's move
So
on.
if it were like 2c, then it would be incorrect?
You're right. So if there was a 2 right here, I would multiply the entire thing by 1/2, and I would multiply this by 1/2 as well.
Oh.
But, and I know this wasn't your question, but I'm going to go ahead and answer the question that wasn't asked. If the 2 was up here, the correct number would be 2, and then we would multiply the whole thing here by 2. We're going to get to a few of those examples, but does that answer your question? I'm hoping yes.
Yeah, it does.
Oh, okay.
Sorry, thank you.
No worries. All right, so now let's take a look at our next one. Get all these highlights out of our way. All right, so the next one is the diamond. And we've already used the first equation, so I'm hoping we find diamond in the second one. And there it is. And I always look to see if there's any other, in this case, diamonds to cause us problems. So I'm looking to see if there are any diamonds here or over here, and there aren't. Now, are the diamonds on the correct side of equation number 2? Excellent. So I'm hearing no. So what that means for us is we need to flip it over. So that arrow, I know it looks like I'm saying oxygen and CO2 only. Let me go ahead and give us some more room here. What I'm saying is we are going to take all of our reactants and all of our products and we are going to flip them over because it's on the wrong side. Now, do we have the correct number of diamonds? What do we think? Yes, we do, because there is an invisible 1 in front of the diamond in the overall, and there's an invisible 1 right over here. So I see 3 of you saying yes. So is everybody okay with us saying we have the correct number of diamonds? Okay, so we got a few more. Excellent. All right, so what we need to do for equation number 2 is we are going to flip it. And when we flip it, we also flip the sign. So that is another way of saying we multiply by a -1. So we will change the negative to a positive. So I'm going to write a little note here that may or may not help. Hopefully it will. When you flip, also known as invert, the equation, you flip the sign of delta H. So that is to say, we multiply it by a -1. So multiplying any number by -1 changes that sign. So any questions about what we're going to be doing with that equation number 2, that because we need to flip the reactants and products, we are going to flip the sign, changing it from a negative to a positive? All right, so let's give this a try. So I am going to flip over that equation, and I'm going to say it is CO2 going on to form C as a diamond, and I'm going to go ahead and abbreviate that, plus O2. And now I'm going to say that we have negative delta H2 because I'm changing its sign. And it is going to be plus 395.4 kilojoules like so. So I inverted, or I flipped the equation. I made products reactants and reactants products. When we did that, we multiplied, oops, let me get a better color there. We multiplied by a -1, and the result of that was the sign changed from a positive to a negative. So any questions on what we did here to write out that equation number 2 in essentially the opposite order with product, what were the products are now the reactants, what were the reactants are now the products? I see a question, just the sign of kilojoules, not the whole equation. You are right, because we could never have negatives here, because this is these are quantities, so we could never have a negative there. So just multiplying the negative right over here. All right, so other questions so far? All right, so now what we are going to do is we are going to add things together, but before we do, we need to cross out anything we see on the right and again on the left. So last slide we said that if you have an oxygen on the right and an oxygen on the left, they cancel out. And now if we have a CO2 on the right and a CO2 on the left, yep, I see. Tasso said CO2 and oxygen, excellent. And then we bring down everything that's left over. So C is graphite, goes to C as a diamond. Now my very strong recommendation is before you do any addition with the math, you compare this to that overall reaction. All right, so we ended up with carbon as graphite, goes to carbon as a diamond, and I go all the way up to the top, and I make sure that this is correct, and it is. Now we're going to add up what we have here. So we're doing negative 393.5 kilojoules plus our positive 395.4 kilojoules. So let's see, if we have negative 393.5 and we add in 395.4, it looks like we have a difference of 1.9, and it appears that this is a positive 1.9. Any questions on how I added up those numbers or how we did anything else? All right, this 1.9 represents the delta H for the overall reaction. Because we have 3 reactions here, I'm going to go ahead and specify this is delta H overall. And it is a positive 1.9 kilojoules. You don't have to put in the positive. I just did that for emphasis. If you say 1.9, I'm going to assume you mean positive. But since it is positive, what can we say about this chemical reaction? Endo or exothermic? All right, I see lots of endothermics. Perfect. All right, so I know Hess's law is not the easiest concept, especially when you're first learning it. So questions on anything that we've done so far? Okay, let's go ahead and take a break. So it's almost 6:55, so let's come back at 7:05. And I will be here. If you have any questions, feel free to type in or just unmute yourself.